Okay, in this video we're going to work through numbers 4 and 5. They're both dealing with parameterized curves. So in number 4 we have a curve parameterized as you see here, and we're asked to find the equation of the curve in Cartesian. That means we want y to be a function of x. Okay, so to do that it's pretty straightforward, and you can see over here. So I have these two pieces. I'm going to solve my equation here for t. So when I solve for t, of course I square x, so I've got x squared, which equals t squared minus 9, and so then I add 9, and then of course I take the square root, and then I have positive and negative. So t equals the positive negative root of x squared plus 9. Okay, then of course I'm going to plug that in for t here. So I have the positive and negative, all that squared plus 11, and that's all taken to the square root. Okay, the positive and negative here, but they get squared, so it's kind of, you don't have to worry about that. And then, so I'm taking the square of a square root, so I get x squared plus 9 plus 11, so I get y equals the square root of x squared plus 20. And the thing here to note is that we want our x's to be positive, because that's what we were limited to earlier. Okay. So we've got that, and just to see that here, we have this bit here, and you can see now that's based on our parameterized curve here. And then if I put in the Cartesian curve, you can see that lays on top of it. But we want to kind of get rid of that negative part. We want it to move on. If I change this, you can see that if I have negative 5, maybe change that to 15, that it still stays in the positive range, obviously, because these are squared. So I have this bit here. Okay, so we've gotten that. The next part of the question says find the equation of the tangent line to the curve at t equals 5. Okay, well if I put in t equals 5, then I put in 5 here, I get 25 minus 9, so that's 16, square root of 16 is 4. Same thing here, get 25 plus 11, so I've got y equals 6. So I'm at the point 4, 6. Well, then you can see from my equation here, I've got y minus 6, and I've got x minus 4. Now since I have this in terms of x and y, I can take the derivative just like that, and that gives me my slope, of course. So when I take the derivative, I end up with x over this. That's the square root of x squared plus 20. I plug in 4 because that's my x value. Plug in 4, so I get 4 over that, 1636, 4 over 6, or 2/3. So then my equation becomes this. And we can see on the graph, this is my particular point here that I saw. So we put it into the parameterized curve, and we get 4, 6. And then we can see the equation is tangent to that very nicely. Okay, so that's number 4. Number 5, we have a different curve. We're going from 0 to 2 pi, and we want to find all the points that are tangent to the curve, where the tangent lines are vertical or horizontal. Okay, and then next we'll find the curvature. Okay, so where the tangents are, so we have this situation here. We have this, we take the derivative, it simplifies, x prime simplifies to t cosine t, y prime simplifies to t sine t. And the thing to remember is, now if we're in terms of our slope here, where we have dy dx is equal to 0, then that's horizontal. That means your dy is equal to 0, and your dx is not equal to 0. If we want our dy dx to equal infinity, then that's going to be where our vertical slope is. That's where our dy is not equal to 0, but our dx is equal to 0. So since we have these already set, we can see that where dy is equal to 0, well, that's t is at 0, pi, and 2 pi. So those are horizontals. And that's based off this right here. And if we use dx from here, we see that that's 0 when t is equal to 0, pi over 2, or 3 pi over 2. Now the thing to note is that, notice we need something to not be 0 here. These are both 0, so you're not going to have a vertical or horizontal at t equals 0. And we'll see that in just a second. Okay. So I have my curve here parameterized. I moved it out a little bit beyond 0 to 2 pi, just so you can see what's happening a little bit past that. Okay. So we talked about, well, let's talk about our 0 point here. So here is our point where t is equal to 0. You can see the parameterized bit of that. Okay, where t equals 0. It's right here. You can see that bit of extra there. That's at a cusp. So that's not going to be, pretty much any line through there would be tangent. It would only touch at that point. Okay, so we have that one. Then we noted that our horizontal should be at pi and 2 pi. So let's go look at pi and 2 pi. Okay, you can see that. That makes sense there. Makes sense there. Good, and our verticals should be at pi over 2 and 3 pi over 2. So we have those as well, and you can see how those work. So we got those, and I'll just put in those extra pieces, and you can see that that one is just not going to fit the way we want it to. Okay. And then the next part, so that was vertical and horizontal points, and now we want to find the curvature. The thing to remember is this formula for curvature, and this is x prime, y double prime, y prime, x double prime, so those are the first derivative, second derivative. Here you have the first derivative of x squared and the first derivative of y squared, raised to the all of that raised to the 3/2. So once we find the second derivative for each one, which we have here, we can just put those pieces in. Now the nice thing here is that you have, so you'll notice we'll have t squared cosine squared t here. We'll have plus t squared sine squared t here. So those two terms together, we've got a cosine squared plus sine squared. So that's going to be 1, and they each had a t squared. So we have a t squared there. And then we have this other piece here that's, this is t cosine sine. And then here we have minus t sine cosine. So those cancel out. So in the numerator we just had t squared. Here we have a similar situation. We've got t squared cosine squared plus t squared cosine squared. So we've got t squared, and that's raised to the 3/2. So then that's t cubed. So we had t squared over t cubed. So our k, our curvature, equals t to the -1. And just remember that the reciprocal of that is our radius, and that's then t. So if we look at that curve, we've got this curve here, and this is our tangent line, and I've just put p's here instead of t's, just so I could have this slider work for us. So I'm just going to play that through, and you can see how that follows along. And actually I'm going to put yeah, we'll just leave it there. Okay, so you can see how that follows along the curve as we go. So that's our tangent line. And you can see how when it hits those points we have horizontal, and well, I can't get it, but it's vertical at that point. Okay, the other thing what we can do is, of course, create an osculating circle, and we won't get much into that because it doesn't ask us to, but it has a radius r, which is t, and it's, we put this in, that's centered at the point on the line. And if you run, instead of a tangent line, if you run a normal line, and you can get the intersection points with this circle that has a radius r, which for us is t, and then you can find the osculating circle, and you can see as you get closer, especially now, you can see as that goes around, it follows the edge and it approximates the curve at that point. Okay. Good. Okay, and I think that covers all of number 5.